So at this point in your study of correlation and regression, in your calculation of the sample example, you have calculated your Pearson's R correlation and determined that to be 0.94. You calculated your R square, which you determined to be 0.88. And as you know now from reading your book, the R square refers to the coefficient of determination, or in other words, tells you how much of the variance in Y is accounted for by variance in X. So once you've calculated R and calculated R square to determine the effect size for your correlation analysis, and you've determined that your effect size is large enough to warrant this, you can proceed to conduct a regression analysis. You should not conduct a regression analysis if your R and R square are not sufficiently high. But in this case, we have a nice high R and also a nice high R square. So we can proceed with the regression analysis. Now the regression analysis, or calculating the regression line for your correlational study, is a very valuable thing because it allows you to predict values of Y based on values of X that were not necessarily observed in your sample. And you can imagine that in practical situations this is very handy. For example, if you are responsible for determining the likely success of someone in the role of air traffic controller, and you have this visual attention test where you've determined that the R square, the coefficient of determination, is 0.88. That means that's sufficiently high, and it means that you can calculate your regression line and then simply give this same visual attention test to a potential air traffic controller and be able to predict with pretty good accuracy what their radar detection sensitivity is going to be. It's very valuable. So let's go ahead and calculate this through. You're going to see that it's really pretty easy. We have the formula for the regression line here. This is y hat, which it means the predicted value of y is going to equal beta, or the slope, times the x value, the attention score in other words, plus the intercept. In this case, we're using a small letter a to stand for intercept. So in order to be able to get this formula, we first calculate beta, or we first calculate the slope, and then we use the slope in the formula to get the intercept. And then we have those two values, and you can determine any value of y based on a value of x. So to determine first the slope, we take our single r value, which in this case was 0.94, and we're going to take 10.27 divided by 9.59, the standard deviation of y divided by the standard deviation of x, and we'll calculate that through. 9.59 gives you 1.07. And we get 1.01. So our slope for this particular example is 1.01. And now we're going to calculate the intercept now that we have the slope. And the intercept is here, so the intercept equals the mean of y, 22.30, minus the slope times the mean of x, 12.30. And now it's just a simple matter of calculating this through. So we're going to take 1.01 times 12.30 equals 12.42. Minus 12.42, and that equals 9.88. Okay, so our slope for this problem is 9.88. Okay, so Now let's experiment with this a little bit. If you look at your values, look in your book at the values that you observed in your sample, and you'll see that the highest value in the range of visual attention scores that you found was 29, right? And you didn't have anybody who had, let's say, a score of 25. So let's plug in. Let's say that we want to know the radar detection sensitivity of someone who gets a visual attention score of 25. So we take 1.01 times 25. That's your visual attention score, right? Which did not occur in your sample, plus the slope, which is 9.88. Plus the intercept, which is 9.88. And if we calculate this through, we find that 1.01 times 25 equals 25.25 plus 9.88. And we see that someone with a visual attention score of 25 will have a radar detection sensitivity score of 35.13. And of course, it would be up to you as the expert in radar detection sensitivity to know the meaning of this radar detection sensitivity score, 35.13, right? All right. So that's how you use a regression line. And as you can see, in many situations, this could be very, very practically useful.